So today we'll be starting with the next unit that we have, that is neural networks. So today's introduction is about neural networks and some basic, the very first model basically, as part of neural network history is concerned. So we'll begin with the introduction and the biological neuron. We have already seen the biological neuron earlier, so this will be a sort of a revision for us. Then we'll be moving on to that model, which is the very first neuron model, that is the McCulloch-Pitts model, and we'll be solving some problems on the same. So artificial neural networks are basically models of the biological nervous system, and they mimic the working of a human brain. So if we were to define it, then an artificial neural network is a highly interconnected network of a large number of processing elements, and these processing elements are called neurons. These neural networks work on the principle of learning by examples. So we know that whenever we are going to train these networks, we always give a series or a set of examples on which it can be trained. So they are presented with known examples of the problem to be solved, which is known as a training set, so that they understand the problem in some way. They capture the essence of the problem in some way, and that is nothing but the knowledge that they're going to gain about the problem. And after training, the network can be used for solving instances of the same problem, which the network has not seen earlier. So, as we know that neural networks are modeled after the biological neuron, let us first just go through the details of the biological neuron. So, the neuron is the fundamental computing element in the human brain, and there are approximately 10 raised to 11 neurons in the human brain. So communication that is happening between neurons, it happens through a connection network of axons and synapses. And approximately there are 10 raised to 4 synapses per neuron. So there is a huge communication network which is there, which is going to which actually connects the neurons to each other. They are going to exchange information. So that is through axons and synapses. How do they communicate with each other? By means of electrical impulses. So they send out electrical impulses from time to time via this connection network that is there. And there is a chemical environment which surrounds the network of neurons. So this is the typical way in which information is passed on in the nervous system. So the way in which information flows through in a nervous system. So you can see that in this diagram, there are these sensory receptors which are going to actually perceive something from the environment. So they're going to sense something from the environment, and then these receptors, they deliver the stimuli from within the body and from the sensory organs. When the stimuli are going to originate in the external world, so from there they are going to actually uh, deliver these stimuli, and these stimuli are in the form of electrical impulses which convey information into the network of neurons. So there are some elements called as effectors, which are controlled on account of information processing in the central nervous system. Now, these effectors will actually produce the response that that is the response that is generated as part of the stimuli received. So what happens is it's going to receive something via the sensory receptors, and then some communication happens, and then some action takes place with the help of the effector. So that is how it is working. And there is certain level of feedback which is given, some internal and external feedback given, on the basis of which this action is actually going to be performed. So this is how information actually flows in the nervous system. And when we talk about the central element of this system, that is the biological neuron. So this is how a biological neuron looks like. So there are some incoming signals which are received via the via the dendrites of the neuron. Okay, so this we have already seen this diagram earlier. So there are three major sections or regions in the neuron, biological neuron, that is a cell body, the axon, and the dendrites. So dendrites actually are the receptors. They're going to receive the information into the neuron, and I mean other neurons. So it's a network. So it's a network of neurons. So other neurons are actually going to give out some signals, and those signals will be received by the dendrites of a neuron. So the dendrites, they form a dendrite tree, which is a very fine bush of thin fibers around the neuron's body. And an axon actually is going to transmit. The axon is a transmitter. So the axon actually transmits the signal of a neuron. It's a long, this part, that is a long cylindrical fiber which carries the impulses from the neuron, that is the axon. And the contact between the axon and the dendrite is called a synapse. So this contact is known as a synapse. Now there are two types of impulses which a neuron receives. They could be either excitatory or they could be inhibitory. So if the type of impulses are excitatory, then in that case the neuron actually fires, and if the type is inhibitory, they are actually going to hinder the firing of the neuron. So there are two types of impulses which actually come into the neuron. So whatever is the output of the neuron, that is actually equal to the total of the inputs which are aggregated within a short amount of time, and that is known as a period of latent summation. So it will be a cumulative effect of all these impulses which are coming in, which will decide the output of the neuron. So the output of the neuron will be decided after aggregating all these inputs within that short span of time, which is known as the period of latent summation. So what is the condition for firing? The condition for firing is that the excitation should exceed the inhibition by the amount which is called the threshold of the neuron. So there is a certain threshold for the neuron. Typically, it is about 40 millivolts. So whatever excitatory inputs are there, they have to actually exceed the inhibition, the inhibitory uh, aggregation of inputs by this amount, which is known as the threshold. So that threshold of this neuron is 40 millivolts. So that is when actually the neuron will fire. So the the characteristic feature of the biological neuron is that the signals generated do not differ significantly in magnitude. So the signals are almost same in magnitude, but the type of signal could be inhibitory or excitatory. Uh, the signal in the nerve fiber is either absent or has the maximum value. So either there is that it is present or it is absent. Okay, so this actually tells you so that you can model this particular neuron in the form of a 0 1 kind of an input. So either it is absent or present. The information that is transmitted between the nerve cells is transmitted by means of binary signals. So in fact, since this is the case, the very first models that we have, they actually model everything in the form of binary signals only. You have the concept of a neuron which is binary in nature in terms of the response, the kind of inputs that it has, everything is binary in nature. After an axon finishes generating a pulse, it goes into a state of total non-excitability for some time, and that is known as the refractory period. So it rests for some time. That is known as the refractory period. So in this duration of time, it is not going to conduct any kind of signal, even if there is some excitation and intensity which is high enough. Still, it will rest for that much time, and then it will proceed with again firing. So it will fire, then it will rest, then it will fire, then it will rest. So that is how actually it works. So that is about the biological neuron. So so to understand this McCulloch-Pitts neuron model, which was the very first mathematical model, this is a hypothetical example. A similar example I had discussed with respect to a perceptron, but we were discussing about the perceptron neuron, but this example is with respect to how the McCulloch-Pitts neuron is modeled. So consider that a neuron in a bird's brain has two receivers, and somehow these receivers are connected to the bird's eyes. So if the bird sees a round object, a signal is sent to the first receiver, which is called as the roundness detector. And if the bird sees a purple object, signal is sent to the second receiver, which is the purple detector. So there are two receivers. One is the roundness detector and second purple detector. So what we need to do is we want to produce a signal, okay, or an output which will tell the bird to eat a blueberry, but to avoid eating red berries or purple violets. Okay, so we have this kind of table which is ready. So we have these four objects. Let us assume there are these four objects which are possible in the environment, and we are going to detect these whether they are purple or round. Okay, so so blueberry, golf ball, violet, and hot dog. So these are going to be characterized by the features purple and round. So once you characterize these objects in terms of features, that is purple and round, you have to decide whether the bird will eat that object or not, right? Your aim is to decide whether the bird is going to eat that object or not. So uh, the bird is going to eat blueberries and the remaining object it's not going to eat. Okay? So this is the kind of data set that we have actually prepared for this particular example. Now, from this data set, what we need to do is we need to actually represent it in the form of some values, because everything is yes, no. So we can represent it using a 1-0 kind of logic, so Boolean logic. So what we're doing is we just map it to that yes, no to ones and zeros. So yes is a 1 and 0 is a no. So this is the kind of table that you get. So let us assume that somehow a real neuron actually adds the signals for from all of its receivers, and it decides whether to send out a yes or no signal based on the total of the signal it receives. So it's just an adder. Just assume that a real neuron is just going to add all the signals. Okay. So what do we need to do here in this case? We need to decide if the total of the received signals is high enough. Whatever the bird has received, the sum of those signals is high enough. That is high enough meaning some value which it's going to surpass, then it will eat. If it does not surpass that value, it will not eat. So that is what is nothing but the concept of threshold. The threshold that was there in a biological neuron is basically how it is represented here in McCulloch-Pitts model. Okay. So McCulloch-Pitts model, actually what it does is you just assume that you are adding all the signals which are there, and you, based on the total that you're getting, you're going to decide whether yes or no depending on the threshold that you decide. So how do we decide this threshold? This threshold can be decided by trial and error. So what if the threshold is 1? Yes. If I decide that the threshold is 1, so now I know the total. The total is what is mentioned in this column, right? The total for whatever we have decided that we are adding the inputs, the sum. We are just taking the sum of these inputs, right? So this is the total. Total is 2110. So what if the threshold is 1? If we say that the threshold is 1, then in this case, what will happen? The bird will eat the blueberry, but the bird will also eat the golf ball and the violet, which is not what we want, right? So the threshold cannot be 1. So what will be the threshold of this neuron? It will be 2, right? So if it is 2, so what we will do is, if it is 2, then only the first case it will eat. So if the threshold is greater than, if the total that is of the inputs is greater than or equal to the threshold, that is 2, then it will eat. Otherwise, it will not eat, right? So the inputs that are there, they are actually present in our case, in this example. These inputs are excitatory in nature. Why do we say so? Because these inputs are actually causing the neuron to fire. So they are actually going to cause the neuron to fire more. So if it is purple, okay, there's a chance that that object is a blueberry, so it's going to cause it to fire. So it is excitatory in nature. So even if it is round, it is going to cause it more to fire. So that is why these inputs are known as excitatory inputs. Okay, but as we know that in the biological neuron there is one more kind of an input that is inhibitory in nature. So we also need to somehow accommodate these inhibitory inputs into the model. Okay, so this is not sufficient. Whatever we have assumed, now we were trying to design the model, right, for this particular example, toy example that we have. So this is not sufficient because this model is not yet uh, taking care of the inhibitory signals. Okay. So now let us see how to incorporate this inhibitory signal. So now instead of a bird, now you just consider a specific type of a bird, that is a robin. Okay. Now this robin actually has red feathers. So just let us assume it is safe around any red object which includes red creatures such as a cardinal. Just let us assume for this example, say. Okay. Now this robin's brain has a neuron with two receivers which are connected to the robin's eyes. Now instead of a bird, simple bird, now it is a robin. Okay. Now this robin will flee. The robin will flee from any creature that it sees. Okay. Now, if the robin sees another creature, some excitatory signal will be sent to the first receiver, which will try to cause the bird to flee. Okay. So the first receiver in this case, in this problem, we have modified the problem now. The earlier context was the case was the bird had to eat something or not. Now we have modified the problem. Now there's a robin again with two receivers, but the question now, the design that we're going to implement is for the bird to flee. So the signal, the output that is required is flee or not. Earlier was eat or not. Now it is flee or not. Should I flee or not? Right. So this robin will receive an excitatory signal once it sees another creature. So there is one receiver which is called as the creature detector. Let us call that receiver as the creature detector. So this creature detector will cause the robin to flee if it sees some creature. Okay. However, if the creature that the robin sees has red on it, if the creature that the robin sees has red color on it, the inhibitory signal will be sent to the second receiver. There inhibitory signal is going to prevent the bird from fleeing. So the second receiver that we have is a red detector. Okay, and it is what kind of input? It is an inhibitory input. So it is inhibiting our bird from fleeing. So first input is an excitatory input. Second is inhibitory. Okay, red detector and creature detector and red detector. These are the two inputs that are there. So we have this kind of a scenario where the object is, these three objects are given. So there's a black cat, a hot dog, okay, and there's a male cardinal, so another robin. Okay, so if the creature is a black cat, right, it's black in color. So red, and it's since it's not red, so the signal for red is no. So yes, no. Creature is yes, red is no. So the robin has to flee. Okay. In case of male cardinal, creature red yes, so it will not flee. Similarly, in case of hot dog, it will not flee. Right. So which of these is excitatory? Excitatory is one which is actually going to cause it to fire. Cause it more to fire. That is nothing but creature detector. and the red detector is actually going to cause it to stay there, stay back, right? Because it's going to hinder the firing. It's an inhibitory signal. It's going to pull it back. So if red, it's going to pull it back. Okay. So now let us see. So this is a scenario. Now we have represented it, the data that we have with us. But now how do we represent this? How do we represent these two types of signals, excitatory signal and inhibitory signal? So the solution which was provided by McCulloch-Pitts was in the form of what is called as weights. So weights, right? So now what we do is, instead of having only the input values as 1 and 0, the inputs, the binary input values, we also add one more element to our model, and that element is called as weights. Now, what is peculiar about the weights in case of the McCulloch-Pitts neuron model? In case of the McCulloch-Pitts neuron model, the excitatory inputs will have positive 1 weights. The weights are +1 in case of excitatory inputs. And in the case of inhibitory inputs, the weights are -1. Okay. So now how do we proceed from here? Now, instead of taking the exact sum of inputs, what we do is we create or we compute a weighted sum of inputs. Okay. So we keep on multiplying. So we multiply the input with a corresponding weight, multiply the input with the corresponding weight, and get the total. So the total is weighted sum of inputs, right? It is weighted sum. So if you look at this table, so 1 multiplied by 1 plus 0 multiplied by -1, so 0. So answer is 1. Okay. So now you're getting your male cardinal 1 into 1 plus 1 into -1. Output is 0. I mean, total is 0, not the output. Similarly, for hot dog, 0 into 1 plus 1 into -1, that is -1 is the total. Now with this background, the earlier procedure is the same. You again decide the threshold of the neuron. So what is the threshold of the neuron? That is something else that you need to decide. What is that in this case? Can we keep the threshold as 1? Because you look at this particular example, the bird has to flee, robin has to flee only if there's the black cat is there, this first row. Okay. Rest all, it's less than 1. The total is less than 1. Okay. So if it is greater than or equal to 1, signal is to flee. Otherwise, signal is to stay. Right. So threshold of this neuron is 1. Okay. So with this example, toy example that we have seen, actually we have come up with the McCulloch-Pitts neuron model. McCulloch-Pitts neuron model. What we have seen is how actually the reasoning is done in case of how did they come up with this model actually, right? With the help of this example. Now we will actually look at a formal mathematical representation of this model. It's a very simple model. So you have this neuron, right? There's a neuron which is there, and there are different inputs which are connecting to the neuron, and each input is having a weight, right? So each input is having a weight. Now the output that you need to compute, first of all, you need to compute a weighted sum of inputs. Okay. So this is the first formal definition of a synthetic neuron model, which is based on this biological model, and it has simplified many things. Okay, it's a simplified version of the biological neuron, designed in 1943. Okay, and this is how it looks like diagrammatically. So there could be n such inputs depending on how many features there we are going to model. Now, in our example that we have seen, so far we have seen 2 inputs. Okay? There could be n number of such input features which are going to actually decide the firing of the neuron, right? There are so many incoming signals. That depends on what problem you're trying to solve. Okay, so depending on the absence or presence of the input values could be 0 or 1. So that tells you it is a binary neuron. The McCulloch-Pitts neuron model is a binary neuron model. The neuron's output signal, it is denoted by small o. These are all notations. So the inputs are connected by direct weighted paths to the neuron. The weights associated with the communication links may be excitatory, that is, the weight is positive, or inhibitory, weight is negative. There is a fixed threshold for each neuron, and if the net input to the neuron is greater than the threshold, then the neuron fires. If the net input is less than the threshold, then the neuron does not fire. That is how it goes. So this is the firing rule. The firing rule is nothing but the output is 1. Output is set is 1. That means the neuron is firing, has fired, right? The neuron has fired if the weighted sum of inputs is greater than or equal to threshold, and it is set to inhibit or not firing if the weighted sum of inputs is less than the threshold, right? So this is how we actually mathematically represent the neuron in terms of McCulloch-Pitts neuron model. Okay. So for the McCulloch-Pitts model, the weights are +1 and -1. That also we have seen for excitatory and inhibitory synapses respectively. T is the neuron threshold. Okay. So this is a very simple model, but it has a substantial computing potential, and it can perform basic logical operations like and or not. Okay. So provided that its weights and threshold are appropriately selected. Okay. So let us try to actually model these basic logical operations and other logical operations via this McCulloch-Pitts neuron model. Okay. So now first is, let us design a 2 input and logic gate using McCulloch-Pitts neuron. So this is the truth table. Okay, very similar to the bird example that we have seen. Okay, so what is the threshold and what are the weights? So basically, when you're actually solving these problems for McCulloch-Pitts neuron model, what you need to do is, first you need to formulate the problem. That is basically, it will be in terms of binary logic. So you will kind of have a truth table. And then from this truth table, what you need to do is you need to decide what are the weights and what is the threshold of the neuron. What are the weights and what is the threshold, right? So basically, if we write it mathematically, what is the firing rule? The firing rule is W1 x1 plus W2 x2. That has to be greater than or equal to the threshold T. And the inhibition rule is W1 x1 plus W2 x2 is less than T. Okay. So from the truth table of AND, you get these inequalities. Okay. So how do you get these inequalities? You just substitute the values of x1 and x2 in those conditions for firing and inhibition. Substitute the value of x1 and x2 in those equations, right? And how do you understand which is firing and which is inhibition? Whatever is having the in the output column, whatever is in the output column, whichever rows are having the values of 0, those are inhibition outputs, right? So that will correspond to the inhibition rule. and whichever is having output as 1, that is the firing rule, right? So first the AND logic. So first 3 rows are inhibition, and finally the last row is firing. Okay, you get these 4 inequalities. Now what you need to do is you need to find the values of W1, W2 and T which will satisfy these 4 inequalities. That is what you need to do, right?
Yes, ma'am.
So W1, W2 is 1 and T is equal to 2. This is the same problem, in fact, that we had seen earlier, the bird example, right? So solution is this for the AND example. Okay, threshold is 2. W1 is 1, W2 is 1, and threshold is 2. So this is the solution to the AND example. Now, let us try to do it for the OR example. So this is the truth table of the OR gate. Can you tell me what will be the values of W1, W2, T?
Ma'am, we could use the same answer as before, just lowering the threshold to 1.
So W1 is 1, W2 is 1, and threshold is 1.
Yes.
Right. Okay. So these are simple. Next, OR gate, NOT gate. NOT gate. So NOT gate, single input. What is the type of signal to NOT gate? It is inhibitory or excitatory?
It would be inhibitory, right? Because it just suppresses the original signal, the original input.
Exactly. It is inhibitory. So it should have weight as -1, right? Once you have that -1, you will decide the threshold. What is it? Threshold will be
0.
threshold is 0, right? So threshold is 0. Weight is -1, single weight, and threshold is 0. What about the XOR gate? So this is the truth table for the XOR gate. Right? So XOR gate, if you try to use those inequalities, you will see that you will not find any solution, right? So it was not able to solve. A single McCulloch-Pitts neuron is not able to solve the XOR problem. Okay. But later on, it was observed that you can actually solve this problem using a network of neurons rather than a single neuron, because single neuron it is not possible, right? You try any combination, and you know why the case is so, right? The case is because you cannot separate it out linearly. Whatever solution that you're trying to actually have using this McCulloch-Pitts model, it is linear separation. Okay, so it is not possible. But the same thing is possible by using the existing universal gates that we have, and, or, and not, and writing this XOR problem in terms of the universal gates, right? So that is x1 dash x2 plus x1 x2 dash, or complement, right? XOR problem. How do you compute it? You look at, how do you get this equation? Everyone knows this, right? How do you get this equation? You look at the output column, and from the output column you see which is output is 1, right? And whatever is there for that row, whatever values are there for that row, you write in terms of, you remember sum of products? Yes, you all remember sum of products?
Yes.
The sum of products, you express it in that term. You will get an equation in terms of the logical universal gates, basic logic gates that we have, and or not, right? So it is x1 bar, x2 plus x1, x2 bar, right? So that is the solution for XOR. So single neuron, MCP neuron, McCulloch-Pitts short form MCP, it is not possible, but it is possible to solve this problem via an interconnection of neurons. So you know that if this is the form that we have got, so this is a combination of AND gates. So this is AND gates, and one of there's a NOT gate before. There's a not this is AND gate again, and there's a NOT here. So how do you actually draw this model? There is x1, right? There is x2. x1, x2 bar. So there is one neuron which will be the AND gate. There's an AND. This is an AND gate. AND gate. That means this is going to have some threshold, right? And the same, there'll be a NOT gate. This will have some threshold. So the threshold of NOT gate was, we have done it earlier, right? Threshold of NOT gate is 0. And what is the weight of that? It is -1, correct? Similarly, this is an AND gate. What is the weight of AND gate? It is 1, right? And this is also 1, right? The weights. And what is the threshold of the AND gate? It is 2. Yes or no? Similarly, for x2, so this is yeah, x1, x2 bar. So it has to come from here. Just put arrows here. Okay. And just give me a minute, just a minute. Yes. Yeah. So x1, x2 bar. Is this correct now? Similarly, you need x2 going to another AND gate. So x2, x1 bar, right? So this is a -1. This is a 1, right? And this is a 1, right? These two are AND gates. So this, I'll just write here for your reference. This is not, right? This is AND, this is AND, okay? And sum of products. So you have OR gate here. So then here further you have an OR gate. Threshold here is 1, right? Okay, so this is your XOR gate. This will be the output. This complex network actually is the McCulloch-Pitts model or solution to this XOR problem. Fine. Let us move ahead. Let us move ahead and try a more complicated problem. Okay. So now you have to design the McCulloch-Pitts model for a 3-input majority function. Now, what is the meaning of this 3-input majority function? Output will be 1 only when a majority of the inputs are 1. Output will be 1 only when the majority of the inputs are 1. That means 3 inputs are there, right? So say x1, x2, x3. You have, what is the output? Y. What is the output? It is 0. It is 0. Majority of the inputs are 1. That means either 2 inputs should be 1 or 3 inputs should be 1. Are you getting this? Either 2 inputs should be 1, 2 of the inputs, or all 3 should be 1. Okay. So this is the kind of truth table that you get, right? Now how do we proceed? The same way that we proceeded for XOR. Correct? So again, look at these rows where the input is 1. Sorry, the output is 1. Right? There are 4 cases where the output is 1. So what is the equation that you get for the output using sum of products? x1 bar, x2, x3, okay, plus x1, x2 bar, x3, plus x1, x2, x3 bar, plus x1, x2, x3. This is what you get. How do can we simplify this further? Is it possible to simplify this? We can simplify this further.
हम फर्स्ट 2 में से x3 कॉमन ले लो तो XOR गेट बन जाएगा और लास्ट 2 में से x1 x2 बचेगा.
x3 bar plus x3. What is x3 bar plus x3? It is 1, right?
Always true.
Can you simplify further? You have to use that concept of simplification. Whatever tricks you can adjust, I mean, add some term. You can do that. Otherwise, you can use the same equation that you've got. Same equation to design it. You can use it. But if possible, you can simplify it. Okay. And again, this is a combination of AND or NOT gates. Okay. So you use the same concept, the same neurons that you have designed for AND or NOT gates, and just extend it further. Fine. So this problem, you have understood how to solve these problems, right? Okay, so there is a simplified version, AB plus BC plus AC. You can see how it comes. You will have to solve it further. Finally, this problem for homework. You design a McCulloch-Pitts model for 3-bit and 4-bit parity function. Okay, odd parity. The odd parity means output is a 1 if odd number of inputs are 1. Even parity, output is a 1 if even number of inputs are 1. Okay, so if again you have to make a truth table for this and solve it in the same way. Fine. So this I'll leave as an exercise for you. Try solving it. Okay. See, you try to express everything in terms of AND or NOT gates. That is fine. But if possible, simplify it. So if you are able to simplify it to this form, your logic, your circuit or the model becomes less complex. That's all. Okay. So that's all for today's lecture.